I want you to try a thought experiment with me. Picture a shadow on a wall. It's moving, it's shifting, morphing. Maybe it starts as this, fuzzy blob, then it just snaps into a sharp, dark point. Now imagine you are a two-dimensional creature living on that wall. You have no concept of out or depth.
The classic flatland scenario.
Exactly. So you're watching this shadow move, and it just seems chaotic. Sometimes it jumps left, sometimes right. You start inventing rules to explain it.
Right. You build a physics for it.
You say, okay, there's a 30% probability the blob moves left, or there's this mysterious force pulling it down. You build an entire branch of physics based on probability and randomness to predict this chaotic monster.
Because you literally cannot see the object casting the shadow.
Right, but if you could just step back into the third dimension, you'd see the truth. Maybe it's just a pendulum swinging, or a ball rolling down a ramp.
And you realize the movement isn't random at all.
Not at all. It's rigid, it's deterministic, it's following simple, beautiful geometry. The randomness you were obsessing over was just a lack of perspective.
And that is the hook. That is the cliffhanger we are dangling off of today.
Yeah.
Because the text we are covering basically asks, what if we are the wall dwellers?
It's the ultimate existential question. Is the universe actually random? I mean, is everything just a roll of the dice like quantum mechanics has been telling us for 100 years?
Or is it all determined and we just can't see the gears turning?
Well, today we are deep diving into a source that claims the answer is option 3. What we call randomness is just the shadow of a higher dimension we can't see.
We are unpacking a text titled Principia Probabilitatis, or The Mathematical Principles of Geometric Probability.
It was published just this year, 2026, by Khalid Bouzain. And I have to say, purely from a vibe perspective, this is not your average physics paper. It feels heavy.
It is incredibly stylized. It's ambitious.
It reads like Isaac Newton came back from the dead, caught up on modern quantum mechanics, and decided to write a sequel to his original Principia.
I mean, we're talking axioms, propositions, scholia, the whole classical structure.
It feels ancient and futuristic at the same time.
The style is a nod to history, but the content is trying to rewrite the future. Bouzain isn't just trying to tweak the math of physics. He is attempting to prove that probability itself, the very idea of chance, is actually derived geometry.
And his mission is to unify quantum mechanics, thermodynamics, and even gravity into a single theory where, as he puts it,
probability is the shadow of higher dimensional necessity.
The shadow of necessity. That sounds poetic, almost religious, but we need to break down what that actually means for you, the listener, because if he's right, everything we think we know about why things happen is wrong.
To get our heads around this, we have to start with the core philosophy of the book. The author uses a central metaphor that runs through the whole text, which ties right back to your intro.
The shadow.
Probability is the shadow of higher dimensional necessity projected onto the fabric of observable reality.
Okay, let's stick with our wall analogy to map this out. In this book's theory, what is the wall and what is the object casting the shadow?
So the text introduces two distinct spaces. First, you have what he calls the total space, denoted as x to the n.
Okay.
This is the high-dimensional reality where everything actually happens. In this space, the text argues everything is real, everything is smooth, and importantly, everything is deterministic. There is no dice rolling up there.
So that's the real world, the 3D world in our analogy, the place where the pendulum is just swinging.
Precisely. Then you have the base space, or y to the m. This is the lower dimensional world we actually observe and measure with our eyes and our instruments.
Right, our wall.
And the act of observation isn't just looking at things. It is a process of projection. It's squashing that high-dimensional reality down into what we can detect.
And obviously, when you squash something 3D into 2D or, say, 10D into 4D, you lose information. You lose the depth.
Exactly. And that lost depth is what Bouzain calls the fiber. Think of it like this. If you project a 3D cylinder down onto a flat piece of paper, it looks like a circle.
Right.
The fiber is that vertical line above every point on the circle that got crushed down. It's the hidden depth that disappeared during the projection.
So the fiber is the stuff we can't see. It's the information that got lost in the squash.
Yes. And here is the kicker, the definition that sets up the whole book. Bouzain defines probability as essentially our ignorance of where a system is located along that hidden fiber.
Our ignorance.
Because we can't see that vertical line. We can't pinpoint the object, so we say, it's probably here or maybe there. We invent probability to cover up our blindness.
That's a fascinating pivot. Usually we think of probability as a fundamental feature of the universe, like the electron is a cloud of probability,
Yeah.
but he's saying, no, the electron is a specific point, you just have bad glasses.
That is a great way to put it. We lack the coordinate for the fiber, so we see a blur. And this leads to the engine of the book, a formula he calls the effective Hamiltonian.
Now, I was looking at this section, and for anyone allergic to math, don't worry, we aren't going to make you solve for x. But we need to look at this equation because it explains the y. It is H effective equals kappa plus log j pi.
Don't let the symbol scare you. It's actually a cost-benefit analysis.
It looks scary, though. What is it actually saying in plain English?
HF is basically the cost of a probability. It explains why one outcome is more likely than another. The text says this cost comes from two distinct places.
Okay, place number one.
The first term is kappa. This represents intrinsic curvature. In standard physics terms, you can think of this as energy. If a spot in that high-dimensional space has high energy, it's harder to be there. Nature prefers low-energy states. That suppresses probability.
Okay, that makes sense. High energy is expensive. Rocks roll downhill because downhill is lower energy. That's standard physics.
Right. But the second term is the spicy one. The second term is log j pi. This is the geometric cost. It represents the distortion caused by the projection itself.
The squashing cost.
Yes. Scholium 2.2 really drives this point home. It essentially says that geometry acts exactly like energy.
How so?
If the projection map has to spread out a lot, if you're taking a huge area of the big space and cramming it into a tiny spot in our space, that geometric cramming suppresses the probability just as effectively as high energy does.
Wait, let me make sure I have this. You could have a spot with zero energy, totally free in terms of traditional physics, but if the geometry is expensive to project down, if the math is too messy to squash it, it becomes unlikely to happen.
Precisely. The author states, geometry is indistinguishable from energy in the calculus of probability. He is unifying the shape of the hidden dimensions with the forces we see in our world.
So something might be rare not because it's hard to do, but because it's hard to see from our angle.
You've got it. And this isn't just abstract philosophy. The book claims this framework explains the two biggest and usually contradictory pillars of modern physics.
Quantum mechanics and thermodynamics.
Exactly.
This was the part where I started to get skeptical, because usually when someone says, I have a theory of everything that explains everything, it, turns out to be word salad.
I get that. But he actually derives the math, doesn't he?
He does. And he goes after the biggest target first. Let's look at book 2, Physical Realizations. He derives the Born rule.
Which is huge.
Okay, quick refresher for everyone. The Born rule is the golden rule of quantum mechanics. It says the probability of finding a particle is equal to the amplitude of its wave function squared.
Right. And usually physics teachers just say, that's the rule. It works. It matches the experiments. Don't ask why. It's a postulate.
It's the famous shut up and calculate method.
Exactly. Yeah. But Buzane says, no, we can derive this. He uses the geometry of something called the Hopf vibration.
The Hopf vibration. It sounds like a sci-fi maneuver, but I know it's a very specific, real geometric structure.
It is beautiful geometry involving spheres. In this theory, the quantum wave function is real. It lives on a high-dimensional sphere. But we don't see the sphere.
We only see rays of light projective space.
And the hidden fiber, that vertical line we talked about, is the phase of the wave function.
That's the imaginary part, the e to the I theta part that usually disappears when we measure things.
Yes, that's the hidden dimension. And here is the aha moment. When you integrate over that hidden circle of phases, when you sum up the hidden fiber to get your probability, the geometry of the sphere forces the answer to be the square of the amplitude.
So it's not a random rule of the universe.
No. He argues it's a geometric necessity. If reality is a sphere, the Born rule is the only way the shadow can look.
It's like saying, if you project a sphere onto a plane, you get a circle. You don't need a rule of physics for that. It's just how shapes work.
That is exactly the logic. It takes the magic out of quantum mechanics and puts structure in its place.
But then he pivots to thermodynamics. And usually, heat feels very different from quantum waves. Heat is messy. It's atoms bouncing around like billiard balls.
True. But in this framework, it is just a different projection. For heat, we are projecting from phase space, which includes both position and momentum, down to just position.
Right, because when I look at a cup of coffee, I see where the coffee is, but I don't see the momentum of every single molecule inside it.
Exactly. The hidden fiber here is the momentum. And when you do the math, when you integrate over all the possible momenta in the fiber, you get the Boltzmann distribution, which is the fundamental law of heat.
This leads to Scholium 3.4, which I circled in red in my notes. It says quantum averaging and thermal averaging are essentially the same operation.
Yes. They're both just fiber integration.
Oh.
The only difference is the weighting. In thermodynamics, you weight by energy, that kappa term we mentioned. In pure quantum mechanics, kappa is 0, is pure geometry. But the mechanism, the shadow casting, is identical.
That is a huge insight. He's saying that the cold, clean logic of quantum states and the messy chaos of a steam engine are actually the same geometric trick, just viewed from different angles.
It unifies the clean and the dirty parts of physics into one geometric framework.
Okay, so we've got probability as a shadow. But here's where it gets really interesting. Book 3, the dynamics of projection. Because if probability is a shadow, what are forces? Because I feel gravity. If I drop a bowling ball on my foot, it hurts. That doesn't feel like a shadow. That feels like a very real force.
This is the most radical part of the text. The author asks us to reconsider what force actually means. He explains it using Theorem 4.1 regarding derivatives. He says velocity, the first derivative, is blind to curvature.
Blind to curvature. Help me unpack that.
I think about driving a car in a thick fog. You can't see the landscape. If you were just moving forward at a steady speed, you can't tell if the road you're on is flat or if you're actually driving on a giant, gentle curve around the Earth.
Right.
You only feel the curve when you change something.
When I turn the wheel. Or hit the gas.
Exactly. Acceleration, the second derivative, does see the curvature. It feels the deviation from the straight line. And this leads to what he calls the universal acceleration law.
The formula is... well, it's complicated, but what's the headline here?
The implication is staggering. The text essentially claims there are no forces.
No forces. Gravity, electromagnetism, the strong nuclear force, none of it is real.
Not in a total space.
Yeah.
In that high-dimensional reality, everything is moving freely. Everything is following the path of least resistance, what physicists call geodesics. But because we are squashing that 5D or 10D motion down into our 3D world, that free motion looks distorted to us.
So what I see is gravity pulling a ball down.
It is just the shadow of the ball moving in a straight line through a curved higher dimension. The force is a projection artifact, and the text lists them out. Gravity is tidal forces from Riemann curvature. Electromagnetism is the Lorentz force from connection curvature.
It's all just shadows of shape. But there's one specific detail in this section that absolutely blew my mind. The bit about electric charge.
Oh, yes. Electric charge is vertical momentum.
That's the line. Because we usually think of charge as a thing attached to a particle, like, hello, I'm an electron, I'm carrying a backpack, and inside is a -1 charge.
Right. It's treated as an intrinsic property. But Buzyn argues charge isn't a thing the particle carries. It is a description of how the particle is moving in the hidden fiber.
So wait, an electron isn't charged. It's just a particle that is moving really, really fast in a direction we can't see.
Precisely. Charge is vertical momentum. The stronger it moves in that hidden fiber dimension, the more it couples to the curvature, and the stronger the force we observe in our world.
That completely changes how you picture a battery. You're not storing charged stuff, you're storing motion. You're spinning up a bunch of particles in a fourth or fifth dimension.
It creates a beautiful unity. Mass is coupling to space-time curvature. Charge is coupling to fiber curvature. They're all just geometric shadows of motion.
It makes the universe feel so much more mechanical, but in a clean way, like a Swiss watch.
A Swiss watch that we can only see the face of, but not the gears.
Right. Now, let's talk about Book 4. Rigidity and necessity. This is where the math gets strict. Because if everything is geometry, then there are rules you can't break.
Yes. The author asks, what happens if the space has constant curvature? Like a perfect sphere.
And the answer is, you lose your freedom.
You do. The math becomes rigid. If you are evolving on a space of constant curvature, the text proves that the only possible solution for how probability changes is the cosine squared rule.
Which is cosine squared of omega t.
Right. And physicists know this formula. This describes Rabi oscillations, how a quantum state flips from up to down. Usually we derive this from the Schrödinger equation, but this text says, no, you don't even need the physics.
Wait, so he's saying you don't need quantum physics to predict quantum behavior?
He's saying that if the space is a sphere, the probability must oscillate as cosine squared. It's the only shape the math allows.
It's like saying, if you draw a triangle on flat paper, the angles must add up to 180 degrees.
Exactly. You don't need a theory of paper physics or triangle forces to prove that. It's just geometry.
That is bold. It implies that the laws of physics aren't arbitrary. They couldn't be any other way because the geometry won't let them.
Exactly. And this leads to the concept of quantum speed limits.
The Mandelstam-Tam limit. Try saying that 5 times fast.
It's a mouthful. But the concept is simple. In quantum mechanics, there is a hard limit to how fast a system can change from one state to another. You can't just flip a switch instantly. Nature has a speed limit.
And usually we think that's because of energy constraints, right? Like, I can't accelerate my car instantly because I don't have infinite horsepower.
Yes, but Buzerian interprets it geometrically. He says the speed of evolution is bounded by the curvature of the state space. Think of a race car on a track.
Okay, I'm picturing it.
Even if you have infinite horsepower, you can only take a sharp turn so fast before you fly off the track. The sharpness of the curve, the geometry, limits your speed.
So the speed of reality is determined by the bendiness of the fiber.
That is a wonderful way to put it. Reality can only unfold as fast as the road allows.
This is a lot to take in. We've gone from shadows on a wall to hidden fibers to charge being motion to geometric speed limits. What does this actually mean for us, the listeners, the people living on the wall?
If you look at the general scholium at the end of the text, Buzerian reflects on this big picture. He says we are essentially living in a thermodynamic partition of a higher reality.
A partition, like a cubicle.
Like a slice that our brains can handle. It's a humbling thought. We think we're seeing the universe, but we're just seeing the projection that fits in our 3D consciousness.
It reframes that anxiety we all feel about uncertainty. We look at the world, news, the weather, our lives, and ask, why did this happen? Is it chaos? Is it random bad luck?
And this theory suggests it's not chaos. It's necessity. It's deterministic geometry that we just don't have the coordinates to see.
It makes the universe feel a lot more solid. Even the spooky quantum stuff has a solid geometric skeleton underneath.
It does. It suggests that if we could lift the veil, if we could see up into the fiber, the dice rolling would stop. We wouldn't see chance anymore. We just see a beautiful, complex machine moving along perfect lines.
But the text leaves us with one final, slightly provocative thought in the conclusion. And this one kept me up last night.
It is a haunting question. He questions the nature of space-time itself.
Right. Because if gravity is just a projection artifact and forces are just shadows, does space-time as we know it even exist?
Exactly. We assume space-time is the stage where everything happens. But if the metric, the very fabric of space we think we live in, is just another projection, then we might not even be on the wall looking at the shadow.
The wall itself might be a shadow.
A shadow of a shadow.
You might be projections of projections.
It's possible. The real, you might be a high-dimensional geometric structure, and the you sitting here talking to me is just the 3D footprint it leaves behind.
That is heavy. But also kind of beautiful. It's just something to mull over while you're stuck in traffic today. Maybe that traffic jam isn't bad luck.
Maybe it's just a geometric necessity in a higher dimension.
A huge thank you to the author Khaled Bouzayan for Principia Probabilitatis. This is one of those texts that breaks your brain in the best possible way.
Absolutely. It reminds us that there is always more to the picture than what we can see.
Keep looking at the shadows. Thanks for listening to The Deep Dive.
See you next time.